So let's take a look at how to derive the period of a simple harmonic oscillator. I've seen this question a couple times on the AP test. If you don't practice it, you might really be blindsided by it. It's not that difficult, but I think it's good to take a look at the technique that's used to do it. So before we get into that, let me just remind you of what the graph looks like for something that's moving with simple harmonic motion. If you make a position versus time graph, you're going to get this back and forth motion, basically what we call a sinusoidal shape. And the equation for that, the equation in this case for position, looks like this. It's x max, that's the largest x value, it's also called the amplitude, times the cosine of omega t plus phi. And some of these elements here, so omega is something known as the angular frequency. I'll talk about that a little bit later. Basically, its units are radians per second. And see, you can only take a cosine of degrees or radians. You can't take the cosine of seconds. So by multiplying radians per second times seconds, you get units of radians. This is called phi, and it's really just the angle where the object starts. So if it doesn't start exactly at this point, which is what where the cosine starts, you can make an adjustment with that. No big deal. But omega is going to be our key to figuring out the period. And the reason is because there's a relationship between omega and period. When something is a simple harmonic oscillator, it moves back and forth repeatedly. Maybe it starts here, then it moves to here, and then it moves to there, and then it goes back again and repeats that cycle over again. It's kind of like something moving in a circle, that if we have something starting here on a circle, it's going to move to here, then it's going to move to here, then it's going to move to here, and then it's going to move to there. It's a cycle that repeats over and over again. If you want to know how many radians per second this thing is moving in a circle, what you could do is take the distance in radians of once around a circle. That's 2 pi. You can fit 2 pi radiuses around a circle and divide by the time it takes to go around a circle once, which we know as capital T. That would give you the angular velocity. When we're doing the same thing with simple harmonic motion, we call it angular frequency. So this is the relationship between something that appears in this equation and something that we want, which is period. So ultimately, period equals 2 pi over omega. So this is one of the important equations that we're going to be using to solve this. So to get there, though, we need to figure out what omega is equal to. That really comes from not this equation, but the acceleration equation. So if we take the derivative of this, we get the velocity equation. If we take the derivative again, we get the acceleration equation, and that looks like this. Negative omega squared x max cosine omega t plus phi. What I want you to see here is that this entire part of the acceleration equation is exactly the same as the position equation. So I could literally replace this with simply position. I could write a equals negative omega squared x. And this is going to be the equation that we use to figure out what omega is equal to. Your goal, if you get this question, how to derive the period of a simple harmonic oscillator, your goal is to figure out how to look at the equation of the object's motion and put it into this form. That is, having acceleration on one side, x on the other side, and a negative sign there. The negative sign is there. Well, let's look at, I'll show you why the negative sign is there by looking at our first example. So let's say we have a block that's on a spring whose spring constant is k. Let's figure out the period of this situation. Let's say this is equilibrium here, and we stretch it out. We move it an x in that direction. What's going to happen is the spring force is going to try to pull it back that way. Notice that these two things are in the opposite direction of one another. And by the way, acceleration is always in the same direction as the net force. So you can see that the position, the displacement, is in the opposite direction of the acceleration, and that's the origin of that negative sign right there. So what we want to do is somehow get an equation for this situation that looks like this. The way that we do that is that we always start these problems 100% of the time with net force equals ma. So here we're really going to get into it. That was just some background for you. But if you get a question like this, start with net force equals ma. Or I should say, you could also start with net torque equals I alpha if it looks like a problem that's dealing more with rotation than linear motion. But start with net force equals ma. Anytime you use net force equals ma, you should draw a free body diagram. If we draw a diagram of the block when it's at this position right here, it's at this position right here, I'm not going to worry about up and down forces, just sideways forces. Well, the only sideways force is the spring force. That's it. So we can replace net force with the spring force. That equals ma. Now remember our goal. We want it to look like this. Well, we have the a. Somehow we need to get an x into this equation. And you probably remember that the formula for the force that a spring exerts, Hooke's law, is negative kx. Well, now we're getting close. I want to get the a by itself on one side, and maybe I'll move it over to this side too so it really looks like this. Let's do this on a separate piece of paper so we have the room. So again, our equation was negative kx equals ma. So that means that a equals negative k over mx. And remember, our goal is to make it look like this. Well, honestly, it does, in the sense that k over m is just a constant value for this situation. Omega squared is a constant value. Everything else is the same. So that means, and this is always how you end up doing this, whatever the coefficient of x is, that's what omega squared is equal to. So literally, omega squared is equal to k over m. When you compare those two equations, that's the conclusion that you can draw. So omega equals the square root of k over m. And remembering our relationship between period and omega, we end up with period equals 2 pi times the square root of m over k. And that's the answer to the question. So just to repeat what you do there, number one, start with net force equals ma. Draw a free body diagram so you know what the force is. Then find a way to replace that force with something that has x in it. And then rearrange the equation so that a is by itself on one side, x is on the other side, and whatever the coefficient of x is, that's what omega squared is equal to. All right, same process every time. Let's try it with a pendulum. Pendulums have periods, so let's do that. So if the pendulum's hanging straight down like that, that's its normal equilibrium position. Let's say we pull it off to the side. We pull it off to the side a certain angle. We'll call that theta. What's going to bring it back is not so much a force, but a torque that's caused by the force of gravity. Force of gravity is mg. And let's give a label to this here. The string has a length that we'll call L. So this is a situation that I mentioned where we're really dealing more with rotation than linear motion. So instead of starting with net force equals ma, we're going to start with net torque equals I alpha. We're going to have to replace net torque with something. If you remember, torque is equal to R F sine theta. So in this particular situation, R, the distance between the force and the pivot point, is actually equal to L. So I'll replace that with L. The force, of course, is mg. Of course, we have the sine of theta. We should think about direction here, and for this, you have to use the right-hand rule. And since the pendulum is turning this way, I want to curl my right hand's fingers in that direction. That makes my thumb point into the paper. That's considered to be the negative direction. On the other side of the equation, how about I replace rotational inertia with the formula for rotational inertia? For a particle, it's equal to mr squared. And in this case, this can be treated like a particle because its mass is concentrated here and it's rather far from the point of rotation. So m, and instead of r, I'm going to use our symbol L because that's the radius of that situation, ml squared. And then, of course, we have alpha. We can simplify a little bit by canceling out the mass. This L cancels out that square. And again, what's our goal? Our goal is to make it look like this, negative omega squared times x. Although I should mention, in a rotation situation, a can be replaced with alpha and x can be replaced with theta. So that's what we really want to make it look like. Let's see, alpha over here, Negative sign over there. We have G over L, and then we have sine theta. All right, did we do it? Well, it's close, but not quite there. We have the alpha, we have the negative, we have a constant. Here we have theta, here we have sine theta. It would be great if we could just take sine theta and replace it with theta. Well, you know what? We can do it. There's something in math called the small angle approximation. You should know it. It comes up sometimes. And the small angle approximation says that if you're measuring your angle in radians, not in degrees, but if you're measuring your angle in radians, an angle measured in radians is approximately the exact same number as the sine of the angle. For small angles, less than 10 degrees. I should really say what that is in radians, but hopefully you get the point. Try it on your calculator if you want to. Figure out what 10 degrees is in radians, and then take the sine of 10 degrees, and you'll see that they're virtually exactly the same number. So using that small angle approximation, I can literally replace the sine of theta with theta. And once I do that, this equation looks like this equation, and omega squared would be equal to G over L. And so that means omega is equal to the square root of G over L. And then relating that to our formula for period equals 2 pi over omega, we're going to end up with period equals 2 pi times the square root of L over G. There's our final answer. Now, those are two examples, but there are other types of situations that you can encounter where you have to derive a different formula for periods. So you should practice these. Two good ones to practice is if you take a look, 2011, question number 3. That's one that's like this. And so is 2009, question number 2. And on my website, I have links, actually in an email I probably sent to you, I have links to where you can access these old AP physics exams. So good luck with that.